Solve for x. Always check to make sure the solutions you get are in the domain of the function. In order to solve some logarithmic equations, we have to appeal to our logarithmic properties. So with this function, we have log of x plus log of the quantity x plus 3 equals 1. We have two logs in this. They have the same base, but we have two different logs. So we're going to have to combine these together. This is where our quotient and product rules come in very handy. Now, let's actually check what the domain is first, because this first one, since we have two of them, log of x, that tells us that x must be greater than 0. Log of x plus 3, okay, x plus 3 is greater than 0 whenever x is greater than negative 3. And both of those have to be true, so we definitely need to make sure that our values are greater than 0. If values are greater than 0, then both of those are true. That'll be our check at the end. Now, the product rule, because we have a sum of logs would be that we have log of x times x plus 3. That's all inside the argument of our log. Log of x parentheses x plus 3 and all that's in the log. That equals 1. Well, based on the base of our log, that was a common log, we could write this in exponential form as 10 to the 1 equals x times x plus 3 quantity. Now this is going to be a quadratic function, but we can distribute our x to get x squared plus 3x equals 10, because that's 10 to the first power. Because it's quadratic, we're going to have to subtract 10 from both sides. So our resulting equation is x squared plus 3x minus 10 equals 0. Now we can factor this as x plus 5 and x plus 2. Those two separate factors. Parentheses x plus 5, close parentheses. Open parentheses, x minus 2, close parentheses, equals 0. Now, each of those individually are equal to 0 whenever x is equal to negative 5 or positive 2, respectively. Those are the solutions to our equation, the quadratic equation we have. But we need to make sure that our values are greater than or equal to, or actually just greater than 0, because we have that vertical asymptote on logs, which means that our solution is actually x equals 2. X equals negative 5 would cause a domain error or undefined error in a calculator if you were graphing or typing in that way. All right, our last example for this, solve for x. Always check to make sure the solutions you get are in the domain of the function. You have log base 3 of the quantity 2x minus 1 minus log base 3 of the quantity x minus 4 equals 2. We can use our logarithmic properties to combine these two logs. And this, because we have a difference of logs, we have subtraction there, this will be the quotient rule. So we have log base 3 of a very large argument, the fraction 2x minus 1 divided by x minus 4. I'll close my parentheses, and that equals 2. Now I'm going to write this in exponential form as 3 to the second power equals 2x minus 1 with a denominator of x minus 4. Now rewriting that as 9 equals the numerator 2x minus 1, denominator x minus 4. We can treat this like a rational equation. A rational equation. So we can multiply both sides of our equation by x minus 4 to clear the fractions, clear our denominators. So on the left-hand side, we arrive at 9x minus 36 equals, and the denominators, so they become a 1. So we have 2x minus 1. Now we can solve this by subtracting 2x from both sides. So that would be 7x minus 36 equals negative 1. We will add 36 to both sides so that we have 7x equals 35, and then last dividing by 7, x equals 5. Now I didn't check my domains, these two individual logs earlier. This first one, 2x minus 1, is greater than 0 whenever x is greater than 1/2. And the second one, x minus 4, is valid when x is greater than 4. And since 5 is greater than 1/2 and 4, x equals 5 is a valid solution.